Sketch a PV diagram of the following cycle. An ideal gas expands isobarically at a pressure P1 from volume V1 to V2. The pressure is then reduced to P2 by an isochoric process. Finally, it's brought back to its original volume and pressure V1 and P1 by an isothermal process. On the diagram, shade the area that represents the net work performed in the process. We say that the ideal gas expands, which means that V2 is going to be greater than V1. And it expands isobarically. So that means that the pressure is going to be constant. In step 2, they say that the pressure is reduced to P2 by an isochoric process. So I know that P2 is going to be less than P1. Now the last step is that we have an isothermal process, and I'm going from its original volume, I'm going from V2 to its original volume V1 and back to its original pressure. So now let's sketch this pressure volume diagram. Let's select a P1 that's going to be bigger than P2. P1 is going to be up here. P2 is going to be over here. And let's select a V1 which is going to be smaller than V2. So I'm going to have a V1 and a V2, and these numbers might be something that you could calculate if you were given numerical information. Alright, so we're going to start at point P1 and V1. So our starting point is going to be up here. And I expand isobarically, so at constant pressure, until I get to V2. I'm going to go from this first point, which I'll call point A, to point B, and this represents my first step. Step 2, I'm going to go to P2, which is going to be down here, and I'm going to do this in an isochoric process. So I'm going to stick at V2, I'm going to stay in that, and I'm going to go down to pressure P2. So my second step of my process is going to look like a vertical line that goes downward. The third step of the process is an isothermal process. Isothermal means an inverse process, and so I'm going to go from this point where I ended here, from point C back to point A, and I'm going to do it in an inverse sort of way. So my third step in my process is going to be along this isotherm. Now we're asked to shade the area that represents the net work performed in the process. Well, it turns out that the net work is going to be the work that's done during process 1 plus the work that's done during process 2 plus the work that's done during process 3. What is the work? Well, the work is the area that's under the curve of the process. The work that's done during step 1 is all of this area that's in red here. The work that's done during step 2 is going to be 0 because there was no change in the volume. And you can see that easily because there's no area underneath that line that's the second step of the process. Now what about step 3? Well, in step 3, the area that we're looking at is going to be a negative area because basically my initial volume is larger than my final volume is. So what ends up happening is I get this green area, but it's going to be negative because the volume is becoming smaller and smaller. So what is the net work going to be? The net work is the sum of all of those three put together. An ideal gas is slowly compressed at constant pressure of 4.04 times 10 to the 5 kilopascal from 10 times 10 to the minus 3 cubic meters to 3 times 10 to the minus 3 cubic meters. In this process, heat is allowed to flow out of the system and the temperature decreases. Next, heat is added to the gas as the volume is held constant. The pressure is allowed to increase until the temperature of the gas reaches its original value. The diagram represents these two steps. In part A, determine the total work done by or on the gas, and B, determine the total heat absorbed or given off by the gas. Alright, so we have this diagram that shows these two steps. In this first step, they say the gas is slowly compressed, and it's happening at constant pressure. So I have an isobaric process, and that process shows me from my start here to the end of that point. So if we call the starting point A and the ending point B of this isobaric process, then I can see that the amount of work that's done by the gas is going to be negative because my final volume is smaller than my initial volume. Then, when I go to this next step, what ends up happening, I get heat added to the gas and the volume is held constant. Well, if the volume is held constant, that means there's not going to be any work done by the gas because it can't expand. So when I go from point B to point C up here, then this is an isochoric process and there's no work that's being done. Now they say that the pressure is allowed to increase until the temperature of the gas reaches its original value. So what they've shown here in this diagram is an isotherm. That's what this curve is sometimes referred to, so that the temperature at point C and the temperature at point A are equal to each other. So that's the reason that they've sketched that dotted line in there. Okay, so let's figure out how much work is done and the total heat. Step 1 we said is isobaric. I'm told that the final volume during this step is 3 times 10 to the minus 3 meters cubed. The initial volume is 10 times 10 to the minus 3 cubic meters. So the work that's done by the gas during this process is going to be P times delta V, which is the pressure times the final volume minus the initial volume. So now I can put in the numbers. The pressure is 4.04 times 10 to the 5 Pascal. Now notice that's not kilopascal, but Pascal, so there's a mistype in the problem statement, times the final volume, 3 times 10 to the minus 3 cubic meters, minus the initial volume, 10 times 10 to the minus 3 cubic meters. And now let's put these numbers into the calculator. I get that the work that's done by the gas in the first step is negative 2828 joules. Now let's look at the next step. During step 2, how much work is done by the gas? Since step 2 is isochoric, delta V is equal to 0, which means that the work that's done by the gas, which is P delta V, is also going to be equal to 0. So the work that's done by the gas in step 2 is equal to 0. So now we want to determine what the total work is that's done by the gas. So I'm going to add those two things together, which is negative 2828 joules, that's the work that's done in step 1, plus 0 joules, which is the work that's done by the gas in step 2. So I get a total of negative 2828 joules. This is the work that's done by the gas, which implies the work that's done on the gas is positive 2828 joules. That's the answer to part A. Part B says determine the total heat absorbed or given off by the gas. We know that we go back to the original temperature, then I know that the change in the temperature during the whole process is equal to 0 because I'm back to the original temp. If that's the case, and I know that the change in the internal energy is 3/2 times nR delta T, then that must mean that the change in the internal energy is equal to 0. Well, what does the first law of thermodynamics say? If the change in the internal energy is 0, then what that means is that the amount of heat that flows into the gas is going to be equal to the negative of the work that's done on the gas, which is negative 2828 joules. So that must mean that the amount of heat that flows out of the gas is plus 2828 joules. So during this process, I had heat that was leaving the gas. Here's the last numerical example. An ideal gas expands slowly to twice its original volume, doing 800 joules of work in the process. Find the heat exchanged and the change in the internal energy if the process is A, isothermal, and B, adiabatic. So let's think about what's going on here. We have a certain starting situation. I don't know what the pressure and the volume are, but they're a certain amount. Then, during the process, what ends up happening is that the gas does 800 joules of work. So the work that's done by the gas is equal to plus 800 joules. And then at the end, what we know is that because the gas expanded, the volume at the end is going to be greater than the volume at the start. Now, we're asked two questions. We're asked to find how much heat was exchanged during this process and what was the change in the internal energy. And we want to know it when the process is isothermal, so that's part A, and what it is if the process is adiabatic. So let's start with the isothermal process. If the process is isothermal, then what that means is that delta T is equal to 0. Since delta U is 3/2 times nR delta T, then that means during this process delta U is equal to 0. So there's an answer to one part of the question. Now the second part of the question says, what about the heat exchanged? Since they told me how much work was done by the gas, the work that's done on the gas is the negative of the work that's done by the gas. So that's equal to negative 800 joules. Well, since I know that the internal energy change was 0, then what that means is the amount of heat that flows into the gas is going to be equal to the negative of the work that's done on the gas, which is negative of negative 800 joules. So the amount of heat that flows into the gas in this type of process, this isothermal process, is plus 800 joules. Now let's look at the adiabatic process. The definition of the adiabatic process is the amount of heat that flows is equal to 0. So the amount of heat exchanged is going to be 0 in this particular part. So that answers one part of the question. Now what about the change in the internal energy? Since the heat that flows into the gas is 0, then that must mean that the change in the internal energy is going to be equal to the work that's done on. Well, the work that's done on the gas is negative 800 joules. To answer this part of the question, the change in the internal energy is negative 800 joules for an adiabatic process. That answers this particular question.